Hi, in this lecture video, I will discuss the movement of electrons in resonance structure. So first, I will describe what resonance structures are, and then I will go over the different rules for drawing resonance structure here in organic chemistry. So let's get started. So first, let's define resonance structures. Resonance structure are basically the different way of distributing electron in a molecule without affecting the identity of that compound. So in an organic molecule, it can consist of a lot of atoms and having different types of electron in them. And it's then possible for us to basically move or push the electron from one atom to another atom without affecting or changing the identity of that compound. But now, not all electrons can be moved in resonance structure. Only pi electron or pi electrons are basically electron in the p orbital. So only this electron right here can be moved around to give rise to the different resonance structure. Moving any other types of electron will break bond, and that will not be considered to be resonance structure anymore. And the significance of being able to push electron around to produce different resonance structure is that it allows the electron or the pi electron to be spread out, and then that reduces the electron density on any part of the organic molecule, and therefore making the molecule more stable. For an example, here is ethoxide right here, and in the case of ethoxide, this molecule right here cannot form resonance, so no resonance. And we'll see why this cannot form resonance later when we discuss the rule how to draw resonance structure. But because this ethoxide cannot form resonance structure, the electron would always localize or locate on this oxygen right here, and then that would then create a very high electron density surrounding this oxygen, as shown here on the electrostatic potential map. And because due to the build-up of high electron density on this oxygen, it makes this molecule right here unstable or reactive. When we compare this with a different molecule, in this case right here, this is acetate. Now, acetate, due to the bonding of it and this group in here, it is possible for this molecule right here to form a resonance structure. And one way to draw resonance structure with this molecule is as follows. We'll take the electron from this oxygen and we donate this up, and that's how the arrow would go. And the products of what we would create following this arrow will be as follows. And this would then be the two resonance structures right here that is significant for this molecule. So what this is showing is that on the very first molecule, the electron is located on this atom A. And let's say here it will be the oxygen B. Now, after we have drew the other resonance structure, the electron now end up on the atom B, or the negative charge end up on the atom B, and now the atom A would be neutral. And both of this resonance structure here are equally stable, meaning they both exist. So basically 50% of the time, the molecule would exist in the top resonance structure, where the electron density locate on the oxygen A. But 50% of the other time, the electron would end up on the oxygen B, because both of this resonance structure right here are equally stable. So in the end, what happening is that the negative charge here on this that this molecule has can be distributed between these two oxygen. And now each of this oxygen right here will then be negative 1/2 negative rather than full negative charge. And again, because both of them takes turn to hold on to the negative charge. And what this allows this molecule to do is that now the electron can be distributed between these two oxygen. So therefore, the build-up of electron and on any oxygen has been reduced by half. And if we were to be looking at the electrostatic map of this molecule, we will then see that now both this oxygen right here has some electron density on them. And this is by far much less compared to the other oxygen over here that is negative, that cannot form resonance structure to distribute electron. And going back to this molecule, this now have wider spread of this electron cloud right here, or it's not as electron rich, and therefore this is then more stable. So resonance is one very important factor that can affect the stability of the set of electrons in an inorganic molecule, and therefore it's very important the student know and recognize how to draw resonance structure and understand the significance of resonance structure. And the more resonance structure that a molecule can have, the more stable it will be. So some molecule can produce perhaps maybe 2 resonance structure, versus other can have 3 or 4. And in general, molecule having more resonance structure will then be more stable. So let's write a few things. So more resonance structure that a molecule can have, then the more stable that molecule would be. And now, in order for electron to move from one atom to another atom in a molecule to produce the different resonance structure, the 2 atoms must be connected through something that we call a continuous path of p orbital. So they need to have a continuous path of p orbital in order for electron to move from one atom to another atom. And this continuous path of p orbital right here means that basically all of the atoms in between the 2 atoms that we're interested in, all of the atoms in the middle must have an unhybridized p orbital in them. For an example, here in this molecule, so let's say we have this molecule, and now let's label this 1, 2, 3, 4, 5, 6, 7. So on this molecule right here, initially starting out, the electrons are basically located on the carbon 1. And now, is it possible that we can now distribute the electron from carbon 1 all the way throughout this molecule and all the way to the carbon 7? And in this case right here, the answer would be yes. And the reason why that is the case is because of the following. In order for electron to be transferred or pushed from carbon 1 to carbon 7, it has to have a path of electron all the way across this bond right here, this carbon chain right here. And we have to now figure out, does this have this path, or this is something we call the p path of electron in it. And again, so that basically means all of the atoms in between the carbon 1 and the carbon 7. So basically carbon 2 and carbon 6, they need to have unhybridized p orbital in them. And now let's check the hybridization of all of this carbon. This carbon right here is sp2, and the carbon 3 is sp2, and the carbon 4, this is sp1, and carbon 5 sp1, carbon 6 sp2, and carbon 7 sp2. So because all of this are either sp1 or sp2, but not sp3, so that basically means all of this carbon right here will still have one or more unhybridized p orbital in them. And because all of this carbon from carbon 2 to carbon 6 have unhybridized p orbital in them, that is the p path that we're looking for in order to push electron from the carbon 1 all the way to carbon 7. So in this case right here, it is possible for electron to push all the way from 1 to 7. Of course, the electron can be donated from carbon 1 to the other carbon in between first, but then finally get all the way to the carbon 7. So there will be a lot of resonance structure that we'll be able to draw for this molecule. But in this case right here, yes, it is possible because there is a p path of electron. Because C1 to C6 all have unhybridized p orbital on them. So this way, very important that we know how to determine the hybridization of the carbon quickly. And now let's now try another example here. So in this molecule, is it possible that we can push the electron all the way from this carbon to this carbon right here? So let's label again. Carbon 1, 2, 3, 4, 5, 6, 7. So is it possible that we can move the electron from carbon 1 all the way to carbon 7 here in this case? So let's analyze this. And again, we need to see whether we have a continuous path or p orbital between carbon 1 all the way to carbon 7. So let's now take a look at the hybridization of all of this carbon. So carbon number 2, this is sp2, and carbon 3, this is sp2 as well. Carbon 4, sp1, and carbon 5, sp1. And now on this carbon 6 right here, this is sp3. And carbon 7 is also sp3 as well. Because the carbon 6 has this sp3 hybridization right here, this it basically ends. So this does not provide that full path right there, all the way from carbon 1 to carbon 7 for the electron to be floating around. So in this case, electron cannot flow from carbon 1 to carbon 7 due to the breaks of this path right here that occur here at the carbon 6, because carbon 6 and carbon 7 do not have unhybridized p orbital on them. Okay, so C6 and C7 basically are sp3, so they have no p orbital in them. So electron cannot flow from carbon 1 to carbon 7. But now, it is possible for electron to be transferred from carbon 1 to carbon 5, but not all the way to carbon 7 here in this case. And now lastly, let's try another example. So let's say here we have this molecule, and in the middle, that where we have the region or the atom with high electron density. Is it possible for us to push this electron right here to the left and to the right of this molecule? And in this case right here, so if here is, so let's label the carbon again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we start at carbon 5, where the electron density is. And now, we can then see that on carbon 4, carbon 3, carbon 2, and carbon 1, all of this carbon right here are sp2. So that would then mean, yes, it would then be possible for electron to be transferred from carbon 5 all the way to the carbon 1. So this would then be yes. But now, how about on the right side? Is it possible that electron can also be transferred from carbon 5 to the carbon 10 in here? And the answer would then be no. And the reason why is, again, at this carbon 6, its hybridization is sp3. So this basically breaks that p path right there. So we do not have a continuous p path. And this is why the electron from carbon 5 cannot be transferred to carbon 10. So that is important for us to recognize that, again, not all electrons can be moved around. And in order for electrons or for pi electron to be moved around to produce different resonance structure, we need to have a continuous path of p orbital on the molecule. And once the continuous path of p orbital are available, pi electron can then move from one atom to another atom they can move at one step at a time. Now there can be many steps that combine together, but they can move only one step at a time, or one tiny step at a time. Basically from pi bond to atom. So that one step, and from atom to bond to produce a pi bond. So that will be the step right here that we see in. And yes, again, it is possible that we can combine many of these steps together, but then that is one step movement of electron right there. For an example, moving pi bond to atom. So this is when we have a pi bond right here, and now the electron can be moved from this pi bond here to one of this atom, either atom A or to atom B. And that's how we can draw that arrow. So that's considered to be one step of electron movement right here. And the consequent, or the products following this arrow, will then be the following. So again, A and B will still be bonded together, but now they bonded together through this sigma bond right here. And A then become positive because A was neutral before, and now B will then have a lone pair of electrons and becoming negative. And the lone pair of electrons comes from the bond pair that it used to form the pi bond between atom A and atom B, and now it ends up as a lone pair of electrons on this atom B. So that would be the meaning of this arrow right here. So that one step right here. And then the other steps will then be electron moving from an atom to a bond to produce a pi bond. So in this case right here, B is rich in electron as a lone pair of electron, and this can then be donated to the bond. So here again, from atom to bond. And following this arrow right here, then we are now producing a double bond between atom A and atom B. So again, each of these are the steps right here, and an electron are moving one step at a time. And this is the one step right here. And we will continue to see many of these steps right here that being combined together to basically produce many other resonance structure in organic molecule.